This is a presentation of the treatment train, an example of one approach to mitigating diffuse water pollution from agriculture adopted by the EdenDTC team. This particular example is located on this farm in the Newbybeck Catchment, one of the 3 study catchments that make up the River EdenDTC in Cumbria, northwest England. The main water quality pressures in the catchment are sediment and phosphorus. High-resolution monitoring at the catchment outlet helped us to determine that high discharge events are responsible for the majority of pollutant exports, and that surface and shallow subsurface pathways, including drains, are the primary transfer routes. As this is principally a stock and dairy farming area, farmyards are identified as key pollution sources due to the large volumes of animal waste generated. In response to these pressures, a number of interventions have been implemented across the catchment aimed at tackling different aspects of the diffuse pollution problem. Pollution sources are addressed first and foremost. These are followed by the targeting of polluted flow pathways using a series of mitigation features. Other interventions, such as stock fencing and tree planting, have also been carried out. This is a concept that we term the treatment train, and the aim of this presentation is to provide an aerial view of a catchment where the approach has been applied. Hopefully this lesser seen perspective will give you an appreciation of the scale and location of the features and how they interact together and with the landscape. Our starting point is on the farm, where separating clean and dirty water on the yard was deemed to be very important. New drains were installed along with improved guttering for 2,340 square metres of roofing, which included the construction of a new roof over previously uncovered yard. 1,200 millimetres of rainfall is the annual average for the area. Falling on an area of 2,340 square metres equates to 2,800 cubic metres of water per year. Separating this water has 2 main effects. It reduces the chance of pollution mobilisation, and it also prevents clean water from entering the slurry store. Slurry storage is an important issue in dairy farming areas, and if stores are getting filled with clean water, then the time that slurry can be stored for is reduced. This in turn forces ill-timed spreading, often in the winter, when pollutants can easily be mobilised and transferred to a watercourse, whilst driving on wet fields can cause soil compaction, which can have further negative knock-on effects on water quality. As we turn, here we get a first look out over the landscape, which you can see is dominated by improved grassland used for grazing and silage production, with some fields in arable rotation. The main land use is dairy and beef and sheep production. The catchment has a clay loam soil that is of relatively low permeability and is prone to waterlogging in the winter, and as a result, the fields are artificially drained. The track in the centre of the picture was identified as a significant pollutant flow pathway. Mitigation Feature One was designed and constructed to intercept runoff from the track. Cross drains were installed to redirect flow from the track into the feature. The feature has a surface area of approximately 185 square metres and a total storage volume of approximately 100 cubic metres, with a contributing area of 1.9 hectares. It is divided into 3 separate cells by permeable rock dams. These are to encourage the majority of sedimentation to occur in the smaller end cell and to make cleaning the feature out in the future easier. We evaluate the effectiveness of this feature by measuring the annual accumulation of sedimentation. Not only can we determine the volume and mass of sediment, but also its chemical properties. In the 2014-15 hydrological year, 500 kilograms of sediment, 2.3 kilograms of phosphorus, and 5.5 kilograms of nitrogen were retained. As we turn to look back down the catchment, we can see more examples of where cross drains have been installed within the track to stop the concentration of runoff occurring and to divert the water onto the field where it can soak away. Coming up in the bottom right hand corner of your screen is Mitigation Feature Two, which was designed and constructed to attenuate flow in the ditch which receives runoff from principally drains and some overland flow. It's a relatively small feature, but there is the opportunity to install more features along the ditch in the future. An annual accumulation of 625 kilograms of sediment was recorded in 2014-15, along with 1.25 kilograms of phosphorus and 2.3 kilograms of nitrogen. At this feature, we also measure inflows and outflows and concentrations, which will allow us to calculate inflow and outflow loads in the future. Over to the left is another mitigation feature, located at the bottom of the hill next to the track. Prior to intervention, runoff used to run down the track and also out of the woodland to the far left. This water used to enter the stream uninhibited. Also, animals gather in this area, which can create a pollution source in itself. Now, Mitigation Feature 3 intercepts and temporarily stores this runoff before it is allowed to return to the stream via an outlet pipe. In 2014-15, the feature retained 1.3 tonnes of sediment, 1.6 kilograms of phosphorus, and 4 kilograms of nitrogen. As we move down the main stream, we can see fencing along the riparian zone, which has been installed across the entire farm. Tree planting has been carried out along the sides of the channel, as well as on the steep slope to the left-hand side. Animals have also been excluded from this slope to help prevent its degradation. In the distance in the centre of the shot, we can see Mitigation 4. This has the largest surfaced area and storage capacity of all the features, partly due to the availability of space. This field margin was previously of little to no use to the farmer, so provides an ideal location for building such features. Previously unchecked flow pathways are now directed into the feature to be temporarily stored. This included a ditch and an overland flow pathway. Flumes and automatic water samplers will allow us to measure pollutant loads for the two inflow and the outflow channels. In 2014-15, this feature retained 2.8 tonnes of sediment, 2.5 kilograms of phosphorus, and 6 kilograms of nitrogen. The aim of this presentation was to demonstrate how the treatment train concept has been applied to a real-life, fully functioning agricultural landscape, and to help show the spatial arrangement of mitigation interventions. Other features that could be used include earth bunds and swales to redirect water, possibly to disconnected upland floodplains, buffer strips with water storage capacity, and also first-order ditches that we feel provide the best opportunity to treat polluted drain flow. The ability of individual features to retain pollutants has been demonstrated. In combination, they stored 5.3 tonnes of sediment, 9.7 kilograms of phosphorus, and 17.8 kilograms of nitrogen in 2014-15. This equates to specific yield reductions of 42 kilograms of sediment per hectare, 0.06 kilograms of phosphorus per hectare, and 0.16 kilograms of nitrogen per hectare at the 160 hectare mitigation catchment outlet. While these combinations combined reductions may seem rather small, it is important to highlight that currently the features only cover 0.02% of the catchment area. The chart to the right hand side shows the performance of each individual feature per unit area. These give average reductions of 26 kilograms of sediment, 32 grams of phosphorus, and 69 grams of nitrogen per square metre of mitigation feature. Naturally, there is going to be variation in their performance. Despite this, we can start to get a handle on the scale of impact such features can have per unit area of mitigation, which should help with the scaling up process and future catchment management planning. However, an important caveat here is that the number of features and their effectiveness does not have a linear relationship, and that there will likely be diminishing returns as the most significant polluted pathways are managed first. GIS tools such as SciMap can be used to identify other connected pathways and topographically suitable sites for future construction of features. We are aiming to develop a model to estimate the type and number of features required in a larger catchment for a required reduction in flow and sediment and nutrient peaks and loads.